Good day, everyone. Now we're about to discuss about power series. So now we consider a more dynamic concept. So it is a series whose terms or functions, specifically powers of x. This is called a power series. So think of it as an infinite polynomial. So this powerful idea will allow us to represent complex functions like e raised to x, sine x, and other as infinite sums of simple power functions, opening up new avenues for calculation and analysis in calculus. Now we have here a theorem. So for a given power series, summation of Cn times x minus a raised to n, where n is equals to 0 and it goes to infinity, there are only three possibilities. So first is the series converges only when x is equals to a. Second, the series converges for all x. And lastly, there is a positive number r such that the series converges if absolute value of x minus a is less than r and diverges if the absolute value x minus a is greater than r. So that are the things that to be considered, or the theorems that to be considered in our lesson this day. Another important things to consider is that let us remember that for a given value of x, the power series becomes a series of constant. So the fundamental question is, for which values of x does this series converge? So the set of all x for which the series converges is called its interval of convergence. This interval is always centered at x is equals to a. The radius of convergence, which is the r, is half the length of this interval. So it can be a non-negative number where r is greater than or equal to 0, or infinity, or r is equals to infinity. So to find the interval of convergence, we typically use the ratio test or sometimes the root test to find the value of x for which the series converges absolutely. So we then must check the endpoints like x is equals to a, positive, negative, or separately, as the convergence tests often give no information when the limit L equals to 1. So the theorem discussed earlier is our guidelines in finding its convergence. So here are some examples. So first example is that find the radius of convergence and interval of convergence of the series summation of negative 1 raised to n x raised to n over n square root of n, in which n is equals to 1. So in our solution, we use first the ratio test with a sub n is equals to negative 1 raised to n x raised to n over n to the 3/3. And next is we set L as limit of an plus 1 over an approaches to infinity. So we substitute our an and our an plus 1. So we have negative 1 raised to n plus 1 x raised to n plus 1 over n plus 1 raised to 3 halves. And for our an, we have negative 1 raised to n x raised to n over n raised to 3 halves, as what we have seen earlier. Now to simply solve the problem, so we rewrite it to its reciprocal. So we have now negative 1 raised to n plus 1 x raised to n plus 1 over n plus 1 raised to 3 halves multiplied to n raised to 3 halves over negative 1 and x raised to n. So we have here now, as we multiply, so we have negative x times n raised to 3 halves over n plus 1 raised to 3 halves. So remaining the limit sign with n approaches to infinity. Now we apply the limit in x. So we have here the absolute value of x. And then we are not yet applying the limit for the n over n plus 1 raised to 3 halves, since both of the n and the n plus 1 in the denominator raised to 3 halves, we can merge it, we can combine it and raise it to both 3 halves. So applying the limit, we have absolute value of x multiplied to 1 as we divide n over n plus 1. We have 1 raised to 3 halves, so we have here the absolute value of x as our answer. So by the ratio test, the series converges when L is less than 1. That is when x, absolute value of x, is less than 1. It diverges when L is greater than 1, or absolute value of x is greater than 1. Therefore, the radius of convergence in the given problem is r is equals to 1. This means that the series converges for sure when negative 1 is less than x, less than, and x is less than 1. We must now test the endpoints x is equals to negative 1 and x is equals to 1. Now, at x is equals to 1, the series becomes summation of negative 1 raised to n times 1 raised to n, as we substitute x as to 1 over n to the 3 halves is equals to the summation of negative 1 raised to n over n raised to 3 halves as n approaches to 1. So this is an alternating series since 1 over n raised to 3 halves is decreasing and the n converges to 0. So the series converges by the alternating series test. So it is also absolutely convergent by the p-series test since 3 halves is greater than 1. Now for x is equals to negative 1, the series become summation of negative 1 raised to n times negative 1 as we substitute x as negative 1 raised to n over n to the 3 halves raised to 3 halves is equals to the summation of negative 1 raised to 2n over n to 3 halves. So we have here the same as summation of 1 over n to the 3 halves as n is equals to 1. So this is a convergent p-series with p is equals to 3 halves greater than 1. Thus, the series converges at both endpoints. So the interval of convergence is negative 1 and 1 close interval. So another example is this. So we need to find the radius of convergence and interval of convergence of the series summation of x minus 3 raised to n over n factorial as n is equals to 0. So for our solution, we first use the ratio test with an over x minus 3 raised to n over n factorial. So we use one of the theorem earlier, so we have the limit of n approaches to infinity, an plus 1 over an. So this is the limit test, and we substitute an plus 1 and the an. So for our an, we have x minus 3 raised to n over n factorial, and for our an plus 1, we just simply add another 1 for us to see if the test is really converges. So we have here x minus 3 raised to n plus 1 over n plus 1 factorial, and for our a sub n, we have x minus 3 raised to n over n factorial. So the limit of n approaches to infinity. So for simpler way of solving it, we can make the denominator into its reciprocal to easily multiply the solution. So we have here x minus 3 raised to n plus 1 over n plus 1 factorial multiply to n factorial over x minus 3 raised to n. So as we multiply it, it remains limit of n raised to as approaches to infinity x minus 3 over n plus 1. So we have here for the limit of x minus 3, we have absolute value of x minus 3 for the limit of, and we remain limit of n approaches to infinity, we have 1 over n plus 1. So applying the limit for the 1 minus n plus 1, we have 0. So x minus 3, absolute value of x minus 3 multiplied to 0 is equal to 0, since anything that is multiplied to 0 becomes 0, right? So since L is equals to 0 less than 1 for all values of x, the series converges absolutely for every real number x. Therefore, the radius of convergence is r infinity, and the interval of convergence is the open interval negative infinity to infinity. So one more example is that summation of n factorial multiplied to x raised to n as n is equals to 0. So for its solution, we use again the ratio test. So we let a sub n is equals to n factorial and x raised to n. So by the limit test, we know that limit n approaches to infinity is the absolute value of a sub n plus 1 over a sub n. So we substitute, so we can have limit of n plus 1 factorial and x n raised to n plus 1 over n factorial x raised to n. So we operate it, so we have limit of n approaches to infinity, absolute value of n plus 1 multiplied to n factorial x raised to n times x over n factorial times x raised to n. So we have limit of n approaches to infinity, absolute value of n plus 1 multiplied to x, because the n factorial and the x raised to n are being cancelled, so we remain in this way. So now we apply the limit. So for x, absolute value of x, we separate it and then we find the limit of n plus 1 as n approaches to infinity. So it equals to infinity. So it results that unless x is equals to 0, the limit L is infinite, which is certainly greater than 1. Therefore, the series diverges for all x not equal to 0. So the radius of convergence in this given problem is r is equal to 0, and the interval of convergence consists of just a single point, is the closed interval of 0. So that's all for our introduction to power series. Thank you and God bless.